Welcome to Let's Talk Space Medicine. I'm Kyle Anderson, your medical student slash space nerd host. For your listening entertainment, I gather my other medically inclined space nerd friends to talk all things space medicine. With our powers combined, we have to explore and entertain the medical questions that stand between us and the stars. Today's orbit, space radiation. Don't forget the sunscreen. As a brief disclaimer, anything discussed on Let's Talk Space Medicine should not be considered medical advice and is not a substitute for seeking medical help from a doctor. We are simply interested in entertaining medical topics in the field of space medicine. And today, I'm joined by my good friends Ryan and Vlad, both medical students at Michigan State University's College of Human Medicine, and both rising second and third year medical students. And so happy you guys could join me today.
Thanks, as always, for having us.
Yeah, it's awesome to be here.
Cool. So I'm Ryan, and like Kyle said, both Vlad and myself are students at the College of Human Medicine at Michigan State over in Grand Rapids. I guess I'll just say a few tiny few things about myself since I neglected to do so last time. But my kind of personal interests are space medicine in general, naturally, and I kind of tend to see things through the lens of nutrition. I have a master's in nutrition from University of Michigan Public Health, School of Public Health, and I also just like to think of things from like a psychology perspective. I'm really interested in isolation research in particular on that front, and currently I am taking a year off of med school to pursue research interests, and I am focusing on precision medicine using essentially it's all at home due to COVID, but doing some really cool work on looking into genes and how rare genes might influence things, particularly in the sphere of like space medicine. Go ahead, Vlad, if you want to introduce yourself.
That introduction, I'll follow up. My name is Vlad. I think it's my first time being on the podcast, and I feel like I'm really privileged to be here. I like Ryan and Kyle said, I'm over at Michigan State University College of Human Medicine, and my interests are primarily with med genetics and internal medicine. I'm really interested in seeing what precision medicine can do, especially in the adult population.
Sweet.
And with that in mind, it kind of really starts to fit in pretty well with this topic that we got talking about here today with solar radiation and long-term effects of that on the human genome and kind of cancer development and things of that nature. So I'm really excited to see what we could discuss here.
Yeah,
for sure.
Very excited to have another co-host on the show. Definitely, this podcast is really an extension of my passion for space medicine. So we're always happy to find other space nerds out there. You guys are now my space nerd friends officially, so you can't take that away.
Do we get a badge?
Locked in.
You know what? We could. You know what? My team is working on it myself.
Vlad, your badge is in the mail.
Yeah, it's in the mail. But tell me what you guys have been up to this week and what kind of how you guys are doing lately.
Sure, I'll go first. I have like the room that you see behind me is the place where I've like hardly left in the last week. I just got back from a trip to Chicago to visit my girlfriend out there, and since then I don't think I've left to go. I'm still one of the unvaccinated majority currently, so just doing my best to avoid COVID. Bunkered down in here and. Just really starting the research that I mentioned on precision medicine, which would be, it's actually interesting. I kind of knew this about you, Vlad, that this was like one of your major career interests was like in that realm.
Oh yeah.
This for me has been like, I kind of just started with this research as a fortuitous chain of events, just kind of let it me into it. So it's not something I thought a lot about before, but I definitely think I'm gonna have a lot of a lot of interest in common with you going forward from here, because it's just an incredibly fascinating world to live in.
No, yeah, for sure. Hit me up when you figure out how to write papers, because I'm miserable out there.
Talking about writing science research or what? Like, what are we talking
Yeah,
about here?
it's rough, dude. But I'm like this. I've never written papers before, and I'm trying to write like 3 different articles, and it's something new. Figuring out
Yeah,
how you want to structure the flow, what references you're using, if you're not losing the audience who's reading your paper. There's a lot to
yeah.
work on, a lot to
I think
consider.
science is a language that's foreign to everyone. I think is
Mhm.
like, I don't know who said that, but it makes a lot of sense. It takes a lot of training to even figure out how to do it well, let alone like communicate it or write it well. So I think that's a brick wall that everyone, if they reflect on their career, like has run into that, because it's just not a natural way for us to like explain ourselves or
No,
to fit in with the community or to do all the different things within science. So yeah, that's makes a lot of sense, man.
no,
And
but
I'm actually kind of curious for both of you, like precision medicines. Like, say that's your like undying dream to be a precision medicine doctor. Does that mean you're an internist, like internal medicine, or like can you apply it to every specialty, or like what kind of residencies are you both like kind of eyeing in the future?
well, with me, I'm eyeing. There's a program down at Baylor. It's internal medicine, med genetics together. So I get to sit on both boards, and I get to save a year for both specialties. Whereas if you would take the traditional route to med genetics, you would have to do internal medicine, and then after that, you'd have to follow up with the fellowship, which is an extra year. So that's what I'm thinking. What I want to do. When I think about precision medicine, I don't think it's like a something that like a single doctor would do. It would be more along the lines of just a kind of like a line of thinking, kind of like a philosophy that doctors would end up incorporating into their practice as new information comes up with risk factors, genetic risk factors, the environments that you're in, what medications would work best for you. So you're going to be having your pharmacists, you're going to be having your cardiologists, your geneticists all working together trying to figure out what is the best pathway to a healthy life for each individual patient, as opposed to looking at a cohort of patients and saying, oh, we see a 95% increase in longevity and like 98 reduction in mortality with these kinds of screening tools and medications. Well, what do we do with that percentage of patients that didn't reach that stop us from getting to 100%?
Sure.
Mm-hmm.
Yeah. I think, I guess my answer to that, Kyle, would be, as far as I understand it, you could really be any kind of doctor you want to be. The the kind of people who would be involved in medical genetics, in my opinion, would be the ones who decided to do research in it. I think I think that in the future we'll have a host of tools that every doctor will be using, um, essentially to screen for rare genes. Just to see if specific people are vulnerable to certain things, if we need special medications for them. And of course, this is going to be pertinent, especially to medicine when it comes to space, because we already have tons of selection filters on who can go.
Mm-hmm.
Uh, and if any of the viewers, anyone watching this in the future, has seen the movie Gattaca, I think you'll kind of appreciate almost explicitly, because that's exactly what the movie is about. It's about only sending the people with ideal genome into space. I think that some aspects of that film could be a reality once we're able to effectively screen for these things, if it's not already happening. Um, so yeah,
Of course, you got to be
it's gonna be
extremely
interesting ride.
careful when you're thinking about what is the ideal genome, because oftentimes
Mm,
there's going to be so much bias
yeah,
in how you
yeah,
measure and how you understand and what you think is the best thing to move forward. If
for
you're
sure.
confusing environment with genome, like we've seen already in medical history where a lot of
I
that has
think
already happened. So,
I definitely have a few things to mention on the topic of radiation as well, when it comes to precision medicine. We'll probably do that later on.
mm,
Yeah, I think you both bring up, like, kind of the ability to reach that, like, both the really good positives and the kind of like the dark side of precision medicine, kind of in the same breath. You were like, we have that ability to to personalize medicine in a way where we're going to be able to reach that like last 5% of people, and really just be able to center it around how it's going to be most any medication or intervention is going to be most efficacious for a person. And I think anyone in the medical sphere, or even outside the medical sphere, has heard the term patient centric care, and almost every hospital system probably has some kind of banner or some kind of like newsletter that says we really care about patient centricism, and we really care about patient decisions and all that kind of stuff. So but yeah, actually this it's kind of serendipitous, because during a conference I went to this past week, precision medicine was one of them was a main topic in regards to space medicine. So there was actually a talk given by the Human Research Program, which is like a umbrella under NASA that deals with everything related to how healthy and happy and how well astronauts perform in space. And one of the things that this person talked about was essentially how precision medicine will be kind of pioneered in the space field to start, and then incubated there and developed in a number of different ways that frankly I probably don't understand. And then it'll be it'll be one of these NASA spin-offs that like really being able to hone precision medicine would start there and kind of transition away from that. And I was like, that was one of the coolest ideas I had heard in a while.
Actually, Kyle, I feel like you were spot on with this being a spinoff, and I'll briefly mention my case for why. I think that the whole crux of precision medicine is looking at these, essentially looking at people who are rarities genetically, right? Every individual, we have millions of genes that we vary between, just person to person, and I might have a handful of genes that are rare in a sense that I'm somehow vulnerable to a disease, and this happens all the time. There are all sorts of genes, single genes, for instance, that can, if you have a messed up version of that gene, suddenly you have this disease that you have to deal with for your whole life. But the mere fact that these are rare genes makes them, from a consumer standpoint, not a very viable, answer for a major pharmaceutical company or like a medical technology company to kind of mass produce, because it's by definition a problem of the minority. In other words, not very cost effective for a ton of R&D funding. So I think you're spot on though, because space obviously will have a very good, the space sphere will have a great use for that kind of precision medicine, focusing on individual astronauts and their needs before sending them along missions. It's a very crucial thing.
So I get. Go ahead, Vlad.
Yeah, I just wanted to also just add a little bit more complexity, because oftentimes, like, yes, some of these polymorphisms, single nucleotide polymorphisms is what they're called. Just a base pair like an A, T, C, or G is changed to something else. Those are oftentimes rare. Like, you won't see you'd see one mutation in many millions of people, right? But the fact of the matter is, when you look at certain populations who smoke cigarettes, or who are exposed to like your high fat, high carb American diet, and you're wondering, why do some people develop diabetes and why do some people not develop diabetes, or why do some people get lung cancer from smoking 30-pack after smoking tobacco for 30 years versus some people only smoking tobacco for 5 years and they end up getting lung cancer? Why is that the case? By all means, the person who smoked tobacco for 30 years should have gotten lung cancer but never did. And a way to help explain or kind of tease apart why that's occurring is through precision medicine. there may be some kind of unique little mutation in there that's either protective or makes you really susceptible to these kinds of diseases that plague all people in the world today. And one of the papers that I'm hoping to help on is actually trying to convince people why they should care more about genetic variants, which is what's a part of precision medicine. What is this variation amongst people, and why should we care about it? It's because of the fact that some people are at higher risk for common diseases like diabetes, lung cancer, cardiomyopathy. And through understanding and teasing apart what these mutations are, then we can get a better understanding of what kind of risks that these patients should avoid. Similar to when we're thinking about precision medicine in space, right? The stakes are so high for an astronaut. You have to go through all this training. You got to spend all this money, and then you got to fly off into space, and that's millions and millions of dollars spent on that. You don't want to find out 10 years into a Mars mission that our astronaut or cosmonaut here has risk factors for coronary artery disease and is now getting impacted by solar radiation, which causes coronary artery disease.
For
and
sure.
only to find out this person has a heart attack, 15 years into the Mars mission. You're like, oh, well, that was our engineer that was necessary for developing our air purification systems where we're going to get another one.
Yeah. Dude, I love how we like only just started and we can't even like we've already come so far away from radiation going down the precision medicine route, but I promise and just like that little example that Vlad just gave us, this will pay up. There will be a large payoff at the end of this. We'll all tie back into radiation.
That's exactly the thing. Is one of the papers that I wanted to share today is talking about how solar radiation the mechanisms of how solar radiation causes coronary artery disease. And if you put someone who's at risk for developing coronary artery disease because they have some variant, some kind of mutation in their system, that's a recipe for disaster. Now it is though, to kind of like take a step back on it and I feel be a little bit depressing about it. It's kind of sad to know that in high stakes scenarios for astronauts, that's where we feel the necessity to kind of explore these variants. Whereas we have such a large populations of people who are being affected to this day, and it's kind of hard to see that organizations are not allocating those kinds of resources to help get a better understanding.
We'll definitely hope that here on Earth we figure these things out, and that's the way that it should be. You're right; it absolutely should be like a focus right now, and I think it is. I think it certainly is. It's catching on, at least from my perspective. It seems to be. But there's no reason, and this is something I always like to fall back on when it comes to justifying space stuff. There's no reason we can't do both at the same time, right?
Absolutely.
So NASA and whoever else will be looking into this stuff on the space industry side of things. They'll be doing it regardless of whatever else the field of medicine is doing. And if they happen to come up with an answer for this to kind of mainstream precision medicine sooner, then the consumer or the patient, which way you want to look at it, they'll eventually get this technology.
Yeah, if it makes you both of you guys feel any better, so my work is in bone biology and kind of implant biology and orthopedics, and orthopedics has a reputation for them being kind of cavemen and don't really do that hard of science, or actually I don't know, the science is pretty good, but the kind of like I don't care, just bone and fix and just all that kind of stuff. And one of my personal projects is actually in identifying some of these SNPs in patient serum pre and post operation to see.
Oh wow, that's awesome.
Yeah, kind of predispositions into how they kind of react in an inflammatory sense towards the surgical insult. So
wow, so we're like all kind of in the precision medicine sphere in a way.
I wouldn't consider my precision medicine at all. I'm just interested.
Well, that's like the beginnings right there. Like if you find something weird and you're like, wait a second, this person had a SNP. You notice that 4 people that have a rare SNP, the single nucleotide polymorphism that Vlad mentioned earlier, and all four of those people had a negative outcome after surgery or whatever, suddenly you're like, wait a second, like, we need to look at this.
And it doesn't even have to be like the exact same mutation. It's just even recognizing, oh, there's this gene or these clusters of genes that are related to surgery, like to like resistance to surgery insult. Just I'm making some kind of arbitrary classification of. If there are mutations in there that destabilize whatever product that gene makes you more susceptible to surgical insult. So when you go through and you kind of do your pre-screening for these patients, when you're thinking about doing some kind of surgery on them, you see that there's these mutations that are kind of similarly consistent with destabilizing whatever product it is that you're looking at. You got to be a little bit more careful when you're evaluating whether or not this patient should get the surgery or not.
Yep. Yeah, so I think in summary, like precision medicine, like it feels like it's coming down the pipeline, and maybe it's faster or slower than people care or want it to be, but it's coming, right? It seems like it's coming.
Oh,
yeah.
And
it's definitely growing.
Yeah, if the people at NASA are talking about it, then, and they're not like NASA, in my opinion, is like an engineering company. It's not really. Someone at NASA has actually told me this. Like we're not like a medical community. Like we don't really have the medicine side of things. Like at our core, they're really a bunch of engineers together. And so if they're caring about this through this conference I was able to go to online, then yeah, it's going somewhere. But kind of more into what else they talked about. So here, hopefully everyone can see this. So this conference was the NASA Human Research Program. I actually spelled this wrong. It's the Investigators Workshop, and it was held last week. And it was the first time I'd really had a good hard science conference on space medicine. Like it was actually the first time they had biologists, physiologists, all sorts of people that do medical research actually there to kind of argue their point and try and figure out kind of ways forward to increase the human performance in space. So it was really a fun conference. Got to hear a lot of speakers, and all around it was just, if you want space medicine and you want like to actually like learn about the science that's being done, definitely take a check it out. I think a lot of their YouTube videos are posted on the Baylor College of Medicine site. But one thing that was brought up that from Orbit One was, what are the kind of major risk factors for spaceflight, just to set a couple ground rules. And I'll just kind of go through this for like a good 30 seconds, not too long. But essentially, this was this was a slide in one of the presentations where they go through these 5 major risk factors in spaceflight. And so, obviously, because it's NASA, they have an acronym. It's kind of their thing. NASA's the acronym. Everything's an acronym. So here we have RIDGE, and it stands for Radiation, Isolation and Confinement, Distance from Earth, Gravity Fields, and Environments. So these things were brought up in this presentation as kind of medical risk factors that make the job of an astronaut or a flight surgeon difficult to kind of combat, certain problems. And we pretty much today we wanted to talk about the first one. And kind of last time we talked about environments, gravity fields, distance from Earth. We pretty much covered everything. Kind of as here's like
hard not to do.
Here's the total gambit of all the things that you could even start with on a mission to Mars. But today we're really focused on radiation. And radiation was actually came up in the news as of today. I think their ears were burning. So Wired published an article today at 8 a.m, it looks like, on
Nice.
How NASA may be wanting to kind of reevaluate how their radiation limits are set.
That's super fascinating.
And so
Did they
this
say
is
in
like
the article what the level's going to be? Did they specify or?
Yeah, so they have a nice little fancy picture that they use on most of their NASA stuff. But
That's
this
just so
article,
cool to me.
what's that?
That picture is just so cool
Oh
to
yeah,
me.
let's just
That's
take
like
it
a
in.
classic ISS picture, dude.
Yeah.
I love that one. Or is that is the ISS? I think, right?
Yeah. All right. So
I see
is
this
this
one around.
like? Where would this be?
That
Where do you think that
We'll
would
think.
be?
We'll think on it. You keep talking
Yeah.
about the
that
article, and
I
we'll
think
think on it.
I was
is
like,
that
I love watching the ISS like videos of Earth, and because the ISS kind of comes over. It's at like a 48-degree inclination orbit or something like that. So you actually approach the continents from very like oblique angles. So you have to actually reorient how you look at North America or look at Asia or how you look at the continent of Africa and all that kind of stuff. And it's really fun to figure out like, oh wait, it's like this is like from this angle. I don't know. It's super fun. Anyway,
I'm gonna guess I'm gonna guess that's the Bering Strait
the
in the
Bering
center
Strait.
there. Yeah,
Okay.
I feel I might be
Could it
completely
be
wrong.
like
See,
Sicily? No, it's not Sicily. No.
so the Bering
Is that like
Strait, like you think like this seems a little too, I don't know.
narrow? Maybe.
I don't know. It could be. But anyway, we wanted to talk about radiation today, and this comes out on the day that we're recording, so this is pretty awesome. And pretty much, this article wanted to kind of go into some of these red risks that NASA has kind of identified and published. It kind of wanted to talk about some of the different things that are these weird effects that Ryan and I talked about last time. And it really wanted to talk about, what is their kind of risk stance kind of going forward. And so they ended up proposing a new limit that would be lower than other space agencies. And that it says here they could be exposed up to 1,000 millisieverts, which is a small unit of radiation. And they wanted to kind of see that this was the acceptable risk for a given mission. And so like radiation is like the reason I bring up this article is that it's as very topical. Like this is like probably what space medicine physicians, flight surgeons, people that are doing research probably are most are trying to most handle first, maybe. Because it requires it presents the biggest problem, I think, in a lot of people's eyes. And if you're gonna be if you're gonna be sustained, like have a sustained presence either in Leo, either on the moon or on Mars, the fact that it is sustained means that you have to find a mitigating strategy for radiation. And it's
Nice.
just it's such a it's a large problem that is unsolved. It's not like we haven't figured this out.
Figured it
And
out.
we
I
don't
don't
have
even
a
think we figured it out for Earth yet.
yeah. And actually one thing that kind of comes to mind is that it's kind of what Ryan and I talked about last orbit. The idea that like everything is kind of you're in relation to your craft, like your whatever like your spacecraft. Like your spacecraft provides shielding. It provides it is your house. This is like your craft is going to be the thing that protects you the most from radiation. So it's also
solution.
it's an engineering solution. And actually, what was brought up during this conference was it was called like the backpack problem. And so it's like the backpack that you carry on one of these missions has to be optimized to have certain countermeasures for radiation or countermeasures for these things, but they have weight that comes at a cost that you have to carry. And I thought it was a very definitely something to look into further. But these two people that were talking about risk management really thought of it, really used this backpack problem as like the basis for their ability to calculate risk and to kind of mitigate risk during a lunar or Martian mission.
Kyle, if I can,
Good.
if I might interject real quick, I think I have a little bit of context too, particularly around that number that you brought up, the 1,000
Yeah,
sieverts.
yeah. It's just a
Um,
number otherwise, so go for it.
yeah, so just to kind of open this up, because even as someone who's had a couple years of med school, I don't think I really learned at all at any point about radiation as a hazard for humans, much less like what the average radiation exposure is, or like what an X-ray does in terms of like the dosage, for instance. Maybe if you go into radiology, this is something that's discussed a little bit more, but um, even with a little bit of medical background, I didn't know these things. So I thought I'd look it up before we talk today, and I found out that so the sievert is just one unit of measuring radiation, particularly dose. It's a dose equivalency, I think. There's a bunch of different measurement notations that you'll see out there. There's the sieverts, which we've already mentioned. There's RIM, which is like the common version of that. You've got like at least 6 other different ways that you can measure radiation exposure or dosage on a person. But we're going to try to, hopefully we can stick to sieverts here because that's the SI unit. And I found that I used a calculator online, and I found that my own personal radiation exposure annually was about, 3.23 millisieverts. So that was me. And the average in the US was around 6. And things like being on an airplane, like being, in a place where there's less atmosphere above you, being a radiologist, working in a nuclear facility, being like some kind of weird military nuclear engineer, or maybe even like living on a submarine or something like that. All these are going to affect how much exposure you get. And the fact is that if you don't have all this atmosphere above you, a lot more of the sun's radiation is going to make contact with your body and be able to disrupt the way your cells are working, right? So, like I said, in an entire year, I'm only looking at about 3 millisieverts of radiation exposure, assuming that I'm not like on some kind of radiation therapy or getting X-rays all the time. And then I also found out in an article, actually, if Kyle can pull my article up for everyone to just kind of see. I only mention it briefly. It's not a major thing, but I'll just post it again in our chat. Essentially, China recently landed a probe on the moon, and they were taking radiation doses on the surface. And it's kind of funny because the main reason you would do this is not because you're worried your probe's going to get fried by the radiation exposure on the surface of the moon. It's more so like, okay, what is like having a human on the surface going to look like? Like what kind of numbers are we working here? How many meters of like lunar regolith do we need between a human and the sun in order to like make sure they're not going to just get all sorts of tumors and other problems? And I think the number after I converted it was that, okay, so I'll take a step back. On the ISS, on the International Space Station, apparently they're looking at about an average of 266 millisieverts per year. And hopefully, if these numbers sound outlandish, it's because I think they are. And I'm not sure this is a measurement that they mentioned in this article, that this is an external measurement or an inside under shielding kind of measurement. But this was the measurement they offered for the ISS. And then for the moon, it was 500 millisieverts per year. So, like again, my personal exposure was about 3. So you're dealing with like orders of magnitude greater exposure, essentially.
Fun fact, regarding measurements. Did you know that there's a banana equivalent dose?
Oh, sure, yeah.
1 banana equivalent dose, also known as BED, is equivalent to 0.1 microsieverts.
Nice.
Because bananas have naturally occurring potassium-40, which is a radioactive element.
Nice.
Wow. Love to hear that.
Very cool, right? I mean, how many people are going to stop eating bananas knowing that they're radioactive?
Well, it's funny that there's a banana for scale in multiple senses of the word.
Yeah.
It's like, oh, you get both the size and how much radiation. It's great.
I was just wondering, like, how many bananas would I have to eat to like simulate the radiation dose of being on the space station for a year?
I feel
Yeah.
like you're more likely to suffer from hyperkalemia than you are
Yeah.
from.
Or morbid obesity. I don't know, something in there.
Remember, disclaimer: this is not a medical show. We're just talking about things that are
Yep.
exciting.
We're here to bring the excitement about space medicine. That's
Don't try
it.
this at home, kids.
Try this at home. Eat your bananas.
Yeah,
But
this
yeah,
is a really
that's
interesting article, man.
Yeah,
What's
if
that?
you want to jump, I just thought I would bring that in. It was just published in 2020. China's doing cool stuff. I mean, I think they're going to try to land people on the moon soon, and I'm pretty sure that they made public their plans to do so. Should be cool. But yeah,
Yeah.
so I just want to mention that. You can go ahead with the other
No,
article.
it's a great article, man. I think it's awesome. Yeah, that I feel like it'll be really nice to have a more solid grasp of when nations, especially the U.S. and other obviously other nations too, when they say they're going a place that when they actually go again, because it's like
Yeah.
I have a lot of I'm certainly happy. I'm all for team space. Anyone who wants to, any country that wants to go to space, for not for military reasons, but for exploration, science, discovery. I'm all for it. Any shape or size, if you going for peace and doing that, that's great.
I mean,
So
there is a world convention or agreement not to do military things in space. I think.
yep,
Last I checked, but we'll
yeah,
have to look into it more.
Yeah, last.
yeah.
I
Maybe
was,
there's an
So
I don't
asterisk
actually
that
think,
didn't see or something.
I'm not sure if China is in on that agreement, but maybe if it's like a UN agreement, then I suppose there would be. But anyway.
Anyway.
Actually, Kyle, I'm just gonna jump in one more thing.
go for it.
So on Earth, the main way that people get radiation exposure here that I kind of already talked about, and we're not talking about so much like UV, ultraviolet radiation, which is something you need to worry a lot about when you're on the beach. We're kind of talking more about what's called cosmic radiation exposure, and this I think I actually mentioned before, like, distance meters of things between you and the sun. That's kind of not really the right way to think about it. It's more so the ambient radiation of, I guess, the universe, and maybe a large part of that is related to the sun. I'm not sure on the actual like physics side of things, but it's more so just the environment. So that might be a more important way to think
Mm-hmm.
about it. But one
Yeah.
actually kind of salient thing that we talk about here on Earth is flight attendants and like pilots, because they're closer to the vacuum essentially. They have less above them. They're
Mm-hmm.
chronically up in the atmosphere. But the thing is, with the numbers that they see, and I believe their exposure is about double that what an average person who is mostly staying on the surface sees. It probably depends on where you are in the world, but or in the elevation and such. But I think they see about double, and the evidence on like cancer risk, it seems to show that there are some specific types of cancer that they're at risk for, but for the most part, we don't actually know for sure like the full consequences of like a lifetime of this, or just like a year or
Mm-hmm.
something like that. And I guess the reason I want to mention that really quick is because when it comes to knowing like the consequences of having people in space for prolonged periods of time, we don't even really know yet how it works on Earth. We're like really nowhere close to fully understanding how things are going to play out as soon as people are up there for very long periods of time, which to this point is not something a lot of astronauts have done.
Yeah, I was just to add on to that. The article that you shared, Kyle, the real versus simulated galactic cosmic radiation, kind of touches on a few points that you were talking about. So it's a pretty good segue. Just to answer your original question, where is the majority of the radiation coming from? Well, at least on Earth, we have two types that affect us. It's going to be solar particle events, which is like your solar flares, And then you also have your galactic cosmic radiation. These primarily come from supernova that originate somewhere within the Milky Way. And then we can have both high LET and low LET. LET is linear energy transfers, which is the way I envision it is, and correct me if I'm wrong. This is my first time learning about this stuff. So, but it seems
we're
it's
all
like
learning here.
yeah, it seems like it's we got these particles that are kind of flying through our cells when we get exposed to radiation, and then these cause reactive oxygen species forming and causes nuclear instability. The high LET radiation is kind of like the problematic ones. This is where we're getting our particles, neutrons, and heavy ions that are causing the DNA strand breaks, whilst low energy stuff doesn't really do that as much. But you're spot on with we have no idea how that works on Earth versus how that works into the atmosphere. I mean, the paper was talking about how the majority of the experiments that we look at when we're trying to see what kind of cancers, what's the pathophysiology of radiation exposure, they oftentimes use very high doses of radiation at one time to stimulate some kind of damage in the cells. The
Hmm.
problem is you never get to that high level of radiation out in space. I think our ground level experiments were around like 1,500 to 3,000 milli Geigers, I think, GY.
I think it's
Mm,
gray.
Hooray.
Grays, sorry. Yeah. I'm thinking about the Geiger counter, and it's just the
Yeah,
most
yeah,
fun
it
sound
makes
it
sense.
makes.
Makes
It's
sense.
There
so
you go.
rad.
Yes.
And they only do it
Rad,
like one
also a
time, right?
common unit. Wait, was that an intentional? I feel like I have to point this pun out. Was that an intentional pun?
I mean, it's
It's
whatever
so
you want
rad.
it, baby.
Rad is literally the common unit for gray. Gray is a scientific, the international unit. That's funny. Sorry.
It's whatever you want it. Then we'll leave it up to the audience.
Yeah.
So yeah, I mean, and like that's a problem, right? Because we understand the physiology of like a one-time high level dose, whereas
Hmm.
out our space exploration missions, where we've kind of done some preliminary rodent samples, cell-based samples, we're well below 500 grays over a
Yeah.
long period of time. And you don't really get that same level of transformation and tumorigenesis as you would with the higher doses, but we don't know what's the long term effects
Yeah.
of those.
Yeah,
I'll
I think you.
walk back what I said earlier. It's not that we have no idea. It's more so that we're figuring it out still. That's
Yeah,
walk back.
Yeah, and
we
Vlad, to your point, like it's not like these scientists are like they're not like doing an experiment and saying, oh, we really just want to dose it really, they're not just lazy. Like, I mean, lazy might be a part of it, but there's the reason the limitation exists, that they have to do a high dose over a short period of time, is often due to beam time at some of these national labs.
oh
So a lot of the
right.
time that these experiments are done are either at Brookhaven National Lab, Oak Ridge National Lab. I actually have an experiment that's at Oak Ridge National Lab, as was called, down in Tennessee, and they have these particle accelerators that generate these cosmic rays or these heavy elements or these crazy cosmic energies, and that's where they do these experiments. But beam time is very like hard to come by, and so you're constrained by the amount of time that you can actually do these experiments. So
I'm sure.
it's just kind of it's a limitation of doing these studies and
Gotcha.
probably brought up in these things. But it's not just the fact that they're, you know it could be useful to do a high dose of radiation like this, but its applicability to space, as you rightfully so bring up, is it's because they have this limitation on Earth.
Gotcha. Yeah, I didn't consider the fact that even generating these particles, like you only probably have fractions of a second when you're colliding and developing these kind of like radiation signatures, I guess is a way to think about them, to hit your cells with. Now that makes a lot of sense due to those limitations. If only we could send our cell cultures into space and do that low cost, but limitations, I suppose.
Yeah, I think that's where a lot of the CubeSat kind of style of spacecraft is really going to be cool for as a science experiment. So rather than having to do all the stuff that goes to space station and whatever, like you could have an experiment that is like pretty, load and go, ready to go, and you could just have an experiment that goes up on a CubeSat. So there's a lot of logistical problems with in vitro work in general. Like
Yeah.
like they one thing that kind of shocked me when I first started doing in vitro work was when someone told me that like the time of day that you plate your cells and the time that you treat your cells, if they're mammalian cells, they actually do exhibit some circadian rhythm problems. Like, and they're cells, they don't have like a chiasmatic nucleus, they don't have any sensory organs of any kind. So it's
There's
but that
something
actually can
in the
change.
genes that like responds to the hormones produced by those nuclei.
Yeah, if only
That's
there was
so
a field of
crazy.
medicine called maybe like really accurate medicine. Is that the one that we should develop? Accurate medicine.
It's accurate medicine, is what we'll call it. That's wicked to me.
But yeah, so
I mean,
it's like like there's spaceflight experiments in general have a hard time, even simulating one thing. Like even if you're only curious about radiation, when you go, an astronaut that goes to space is not confronted with just radiation. They're confronted with all 5 of these things at once. The stresses of it, the carbon dioxide, there's a bunch of physiologies that are interacting in here, and if you're really interested in studying radiation, you want to study it in a silo, at least for a period of time, and then you can kind of combine it once you have all the learnings from that. So it seems like I don't really know the right fix. Try what you can and just do the experiments when you can, and know the limitations when you make conclusions. So
Yeah, that sounds like such a nightmare trying to tease out all the mechanisms and potential risk factors and pathologies when you're hit in such a weird environment like space.
So I guess I feel like we've at this point kind of contextualized like what radiation is, where it's coming from, how it looks like where our understanding is at, and how it looks on Earth, and maybe on like the moon. I would imagine the Martian environment because they have a little bit of atmosphere to be maybe a little less than on the lunar surface.
There's not much of
I
it, is
wouldn't
there?
know. I mean,
it's
no,
it's
I don't
about
think there's
it's
all,
about
but
1%, and radiation on the surface of Mars is definitely a large problem. I don't have any numbers behind it, but the effective atmosphere it's like just pesky enough to it doesn't really help you landing on it, and it doesn't really, you can't breathe it, so it's kind of pesky and in the way,
like
and
being annoying a little bit.
it's just annoying, yeah. So it doesn't really provide you much radiation coverage, to the
It's
best of my
probably
knowledge.
also a magnetosphere thing too. I mean, I might just be pulling that out of nowhere, right? But it's not only the atmosphere; it's the fact that we have like the Earth has like a strong magnetic field. I don't know what the magnetic field situation of Mars is. I think my understanding is that they don't have one on Mars or on the
Mm-hmm.
moon.
Yeah,
Yeah,
they
I think
have
that's
like
right.
a magnetic. Oh, I'm sorry. Go ahead.
Well, I mean, I think that's right. I know it's not strong enough to have like the normal like gyros that are on a satellite to that work off of the magnetic field of the Earth to allow station keeping. Like they have like certain gyroscopes that allow you to like essentially to. I need to fix this really quick.
Oh, I
Pretty
see.
much,
Okay.
yeah. Pretty much, you have these gyroscopes on satellites that work off the magnetic field, and I know that around Mars, you don't have either a large enough one or one at all to really have that as a viable thing. But I don't know. Maybe I'm wrong. What were you gonna say, Vlad?
I was just man, I'm kind of kicking myself that I didn't look to understand kind of like how magnetic fields play a role in protecting you from solar radiation, but
I think it's a
some
significant
basic
role.
what's that?
I think it's a significant role. It might even
Oh,
be
it
more important than
certainly does.
atmosphere. But
Yeah, maybe this will be
maybe
a talk for another orbit.
This is a question for the physicists. So I know Kyle's brother is a physicist. Maybe he would know the answer to this, but I don't even know. I'm like, hopefully someone who does know the answer at some point will be able to reach out to us. But I might just be curious enough to try to figure it out on my own later.
Oh, certainly, yeah. I mean, I did a quick glance over a Wikipedia article and take that for what you will.
Mm.
And essentially, it has magnetic field, but it doesn't have like a inner dynamo to produce a large enough magnetic field to shield it from solar radiation. Now, I have no idea what that means, or how that relates to like Earth's inner dynamo. I don't know what's generating that, but
Gotcha.
I think it's the rotating molten core. I think if I remember, high school, what earth science or
either way, like however it works. I mean, you've got atmosphere. You can have more tangible physical barriers like the hull of a spacecraft, a spacesuit, or a magnetosphere. I don't personally know how much each of these is going to affect your radiation dose, but the point is to kind of tie it back into medicine. The point is it's a problem that exists. The engineers can do what they can do to try to minimize the exposure, but for now, astronauts on the ISS, astronauts on spaceships going to and from different planetary bodies, they're going to have to deal with the reality that their radiation dose is going to be higher than we see on Earth, significantly higher. And it's going to be our responsibility as space medicine professionals. I don't know if Vlad is interested. You never mentioned if you wanted to be a space doctor at some point.
Oh no, I definitely want to be involved. I definitely.
But anyway, it's our responsibility to kind of figure out.
That's why I'm here, dude.
Yeah. It's going to be our responsibility to figure out how significant of an issue this is going to be, because we're not just about sending people into space. We need to make sure that they get back, and we need to make sure that we're not significantly impairing their life, essentially their life expectancy and quality of life when they get home. These are things that we need to control for, and it's going to be on the space medicine's specialists to kind of assess this risk and come up with solutions that are not necessarily engineering, but also on the treatment end of things, pharmacology, and other maybe prevention and such.
No, you're absolutely right. I mean, when you look back to the history of science, a lot of discovery that we've made is from things where they've been broken. Right? We see some kind of a disease, we see some kind of exposure, and then it just affects someone really, really negatively. And then from that kind of a tragedy, if you will, we kind of learn our discovery from it, right? And it's kind of we as medicine, as people who are going to be practicing medicine, especially in these kinds of fields, we don't want to send someone who's going to be at significant risk to come back with something horrible for us to learn from. But then, unfortunately,
we want to mitigate that if we can.
We want to it's a responsibility for us. We can't simply just send, astronauts, cosmonauts into space just for them to come back sick.
Yep.
With their life being significantly shortened.
I think this is an attitude that's shared by the majority of space programs. I don't know, where China's human ethics side of things is. Obviously, they've been in the news recently, within a year, I think, for the there's a researcher who used CRISPR technology to gene edit a baby or something like that. So obviously, I mean, that's just one example, and probably doesn't speak to China's way of doing research or their space program by any means. But I think most space organizations are on the page of hey, these people we're sitting in space, we expect them to come back, and we expect them to be in good health when they do come back.
I think we're bringing up that radiation, is a problem. We're not really sure, how it's going to be handled. But if it's all right with you guys, to transition to what happens when you get irradiated? What happens? So what are some of the medical consequences of these kind of high dose radiations? And this is kind of kicked off in this Wired article that we kind of began with, where it kind of talked about the different types of radiations. You have alpha radiation, which is I believe, a 4/2 helium nuclei that is, ejected from the sun. You have beta radiation, which is essentially electron radiation. Gamma rays, which is gamma ray. I don't know how else to describe that.
I think it's like
Energy,
a
huh?
photon, isn't it?
It's of a certain wavelength. Yeah, in the gamma ray.
It's like an X-ray, but taken to the next level.
Yeah,
Even stronger X-ray.
yeah. And
Yeah,
then you
so-
have these heavier elements as well that kind of get ejected from the sun and from different places. Vlad, did you have something to say?
Yeah, I could jumpstart that conversation and talk about cardiovascular disease as I was talking about earlier, and how radiation induces cardiovascular disease, and
I was hoping you
it's like rehearsed, except we didn't
would.
fuse that well. So anyway, yeah, the paper that I was taking a look at called "Radiation-Induced Cardiovascular Disease: Mechanisms and Importance of Linear Energy Transfer" kind of talks about the pathology of how we get cardiovascular disease from radiation exposure. And the long and the short of it is we have low, like I mentioned before, we have low energy and high energy exposure. And the high energy exposure is the one that seems to, at least to me, interest me a little bit more. But before I go into that, if you could scroll down and take a look at that first figure.
Oh, I love figures.
Yeah, I learned this today, and this was really, really cool to me. So essentially, I'm just gonna be drawing
Mm-hmm.
ballistics metaphors into radiation, because that's how that's
Yeah,
what it
you're
seems to
getting
be like,
shot
right?
with stuff. That makes
Yeah,
sense.
you're literally getting shot with microscopic bullets, right? And so that's what that first graph is showing. Your dose delivered, that's how much radiation you're getting shot with. So if someone put a machine gun to you with a bunch of like radiation, they just fired into you. It's not really going to affect you initially with your tissue depth. The deeper and the deeper that your tissue go, that the deeper and deeper the particles go, the less radiation you get, essentially.
Mm-hmm.
Kind of like thinking of it as like your skin is like body armor. As the bullet kind of goes in, it slows down, right? Because there's more stuff getting in the way. Within that next figure, in figure B, this is where something really cool happens. You get this plateau region where the particles start to slow down. And then you get this thing called the Bragg Peak, which describes the phenomenon, well, where you have a radioactive particle. Once it slows down, it kind of stays in that area. And once it's in that area, it now starts to release a lot of radiation. And that's why you get a peak in the dose delivered.
So when you say release radiation, you just mean like the energy that existed in whatever this. So we have like a photon, or what kind of radiation are we talking about again?
I think this is just for any
Photons?
kind of, yeah,
Okay.
photons, electrons, alpha.
It might be generalized to different types.
Sure. Okay.
Yeah.
Or I would guess that
This
it's
is where the energy
particle
is being
particle
released.
radiation, because if it was gamma, it doesn't interact with matter,
Oh, right.
so
Right.
it wouldn't have
Yeah.
a quote unquote slowing down effect. So that would be my guess.
That makes
Please,
sense.
audience members, type in the comments. We'd love to have you. So yeah, you have these particles, and as they slow down, now that they're slowing down, not moving as quickly, they're able to exert their effects more. So now they're kind of like delivering more energy than they would if they were traveling
I
at
like that language.
a higher speed.
So these particles like to brag a lot more, is what you're saying?
Yeah,
Like to
dude.
shout. Can you imagine the guy named Bragg? Like this, there's a person out there named Bragg. He or she like got to name a thing named the Bragg Peak. That's pretty cool. I don't know. That's pretty awesome.
That's what we're all hoping for, is to get our names to describe some phenomenon.
I mean, I hate eponyms, but Bragg Peak is not the worst one in the world.
Yeah, definitely not. So that's kind of like what's happening when you get hit with radiation, right? Like once it starts to slow down, it starts to get really, really bad for you. We scroll down a little bit more now to that next figure where you see two cells. That's going to be kind of like what's going on with A being your low energy, and B being your high energy.
Ooh,
With low
that just looks
energy,
terrifying.
yeah, this is an approach to kind of using radiation for therapeutic purposes, and patients with cancer, for example. If you're trying to kill cancer cells, you take these two different approaches. You could either fire them from a lot of different angles,
Mm-hmm.
and you're trying to just cause general instability, or you fire them really, really hard with a high energy LET. Now, the thing is, the high energy LET is really problematic because it's more likely to cause double-stranded DNA breaks. Once you make those double-stranded DNA breaks, that's when your cell starts to great for treating cancer, horrible for astronauts being out in space. This is where your cells start to um, kind of undergo apoptosis, start to generate a reactive oxygen species. They start to undergo a cascade of death.
And kind of to laymanize that, right? Like, is there a way we can laymanize like reactive oxygen species? Maybe everyone knows
Yeah,
about
so when
antacids
your bullet goes through your
by now.
body, everything just like pops and opens up, kind of like the exit wound being that giant hole in your back. That's what's going on with the cells. It's great.
Yeah.
Not completely though. Reactive oxygen species are more of like a way. We would have to go down a pathway of like describing how inflammation works, but essentially it's like your cells get really really upset and they start to release bleach everywhere.
I think, yeah. The way I think about that is like.
Go ahead.
Oh, thanks, Kyle. The way I think about it is like all of our cells are made up of molecules, proteins, what have you. All those are made up of atoms. All atoms have or I don't know if I can say all atoms. I'm sure there's like physicists out there like mashing their keyboards if where they'd watch this.
Oh my God, Ryan, you suck.
Most atoms have electrons orbiting them. What happens is when radiation, like a photon, a particle, passes through a cell, these beams of radiation are very, very tiny. They interact at very, very specific sites on the atomic level, and they knock atoms off of, or they knock electrons off of certain atoms, and those electrons that are now free, in other words, free oxidants, they can interact with a different atom instead, or they essentially move around to a different place. They no longer have a home wherever they came from, and if they happen to go on to interact with the atom that's supposed to be a part of your DNA strand, suddenly this part of the DNA strand has more electrons than it's supposed to, and that can cause the DNA strand to break. And now your body has to go and fix it. And if it happens to fix it incorrectly, finally, I mean, this is a lot of basic science, but finally you've arrived at a point where
nice.
it's single nucleotide polymorphism, which we mentioned earlier. And you now have a mutation that could be problematic. And if you have a lot of radiation, you get a lot of free radicals, a lot of these homeless electrons, displaced electrons, electron refugees, finding a new home in your DNA where they're going to mess everything up. And this is the sort of event that could cause cancer, could cause a cell to start dividing rapidly on accident.
And if
you're
that's
what I could have done.
No, it's great.
Interpretation.
No, I think it's really important because like what I just pulled up here is like a biologist view of what you just described. And I think even biologists are bored by this. They must be, like when they see when you see this on a lecture slide, it's like, oh, you have a particle that can affect at the cellular level, and you have reaction oxygen species interacting with the mitochondria, causing apoptosis and caspase C expression, and then it causes off-target effects into receptor tyrosine. It's just like, come on, like, dude, just like talk about it, like really talk about it. So yeah, if you're actually a biologist, just take a look at this this article, and yeah, like I thought this was a really really cool article. I'm so happy you brought it up because this was kind of a. You got it, man.
I just wanted to finish up. Essentially, like we're talking about essentially how cancer is formed, right? That's what you were mentioning, right?
Oh yeah, that's one of the
where you get the reactive oxygen species. I like to think of it like acid. The acid starts like cooking away your DNA, and then boom, you got a tumor, right? Whereas in this case, that's typically not the case. Well, I shouldn't say it's typically not the case, but with high energy LETs, what's going on with that is that the acid that gets produced is at higher concentrations, and it just pisses the cells off even more so, especially the cells in your blood vessels. kind of like the little builders of your blood vessels.
Mm-hmm.
It pisses them off to such a degree where they're actually angry for 6 months straight. Or typically when you get like a cut, right? That's the same thing that happens. You piss off the
Mm-hmm.
cells in your leg, and then essentially they're throwing a tantrum, they're super angry, and then they attract. They tell the other cells in your body like, hey, we've got to help these crying babies out a little bit here, and then they give them like the mommy kisses on the cheeks. They put the little band-aid on, and then boom, everything heals up. But if they cry for too long, then you start getting into problems where things don't start healing well. Much like a parent that isn't taking care of their kids well, the kid's not going to be doing well in the long term. Parent needs to be affectionate and giving. If the parent isn't affectionate and giving, the kid's not
So
going to
in
be
this
doing well.
case, in this specific case, the parent being like the rest of the body or like the
Yeah,
immune
the
system
rest of
and
the body,
everything,
right? They're not taking
and
care of the different parts of
kid
it.
is
And
like the cardiovascular cell. Just to make
yeah, and
sure.
so in this case, the kids that are upset are your blood vessels. They're
Okay.
crying and they're upset. And they're crying so much that it's actually starting to cause the same stuff that you get when you eat too much fat, when you smoke too much tobacco. You start to get plaques developing in your blood vessels. Your
Mm-hmm.
blood vessels start to clog up. And this is what's happening when you get exposure to high energy LETs.
Yeah,
And I thought that was
actually.
absolutely remarkable.
Mm-hmm.
That's crazy.
Yeah, I think it was also brought up during this investigators workshop. There was a study that was presented by I think a number of different people because there's many different aspects that you can look at this in a lot of different data sets. But one astronaut, they had a very large blood vessel in your head and neck region called the carotid artery that was like as stiff as it increased the stiffness like it was the age of like a 60 or 70-year-old person from like a 6-month period of space flight. So it like directly had caused this either through a fluid shift problem, which we kind of talked about last time, or a radiation problem that we're kind of bringing up now. And yeah, like actually getting into like cardiac remodeling that this paper talks about, like as the radiation effect. I actually always thought that the reason that your heart in space kind of like remodels and changes shape was largely due to a fluid shift, but it seems like radiation is also could play a role here.
It's always playing a role, man.
Yeah,
Yeah,
Like
it's
things
like
are like every problem has like every every cause, like everything. You can't just isolate a problem, right? Like that's
yeah.
that's the crux of it.
mm-hmm.
Yeah, for sure. And I mean, like I completely believe you, Kyle, when you talk about that there was that patient who had carotid artery that was so much more aged, especially after reading this paper. And it really expands what you think the problems makes you. It really expands your understanding of what radiation can do to someone. Most of the time, you think of radiation, you think of Chernobyl, and you think of boom, you're getting cancer, like thyroid cancer, and take your iodine pills.
Mm-hmm.
Whereas here we're learning about like cardiovascular changes. We're learning about blood vessel changes. I'd love to see what other kinds of things we could uncover and
Oh
discover
my
with
gosh! Actually, I don't
this.
I don't know if this is a good time or if Kyle you have something that you're thinking about, but I also had a little bit of an article to bring up with
Strike while the
another
iron's hot, man. Go for it.
separate consequence.
Yeah, let's go for it.
So it's yeah, like another thing. I'm gonna do everyone who's been like diligently waiting for me to actually deliver the payoff on the discussion about precision medicine, like it's finally time. But this is actually another article from the same source that Vlad linked. I'll just repost it here so Kyle can find it more easily. I think that's the right one. Uh, yeah, so radiation, right? We covered. Pretty much everyone knows that radiation is associated with cancer. Take your iodine pills, etc. As Vlad mentioned. Cardiovascular disease, something is like definitely not the first thing you think of when the topic of radiation is brought up. Another thing that I wanted to quickly mention was the fact that radiation, specifically chronic radiation exposure, has an influence on how your immune system works. So this is just another body system, and the reason I was kind of saying like every problem is caused by every possible cause is because I think that you probably would be hard pressed to find a body system that isn't affected by radiation. And I don't really have the citations to make that claim like as a strong statement, but that's kind of my sneaking suspicion. But to focus a little bit on the immune system, this article right here, it's less a scholarly article and more just like a couple researchers' thoughts on kind of where we're at with how radiation affects the immune system. It's just a couple different things itself. The main reason I just want to bring it up is to quickly just kind of say that when you are living in a space where chronic radiation is your reality, your immune system is not going to behave normally. And this article kind of goes on to say, like, hey, it's not that if you're being irradiated, your immune system is like completely activated in every way, much like when you're exposed to a virus or something like that. Actually, specific cells that fulfill specific functions within your immune system are elevated. Some are decreased, and really the immune system is all over the place. But I thought this was a great opportunity to mention precision medicine because really, when we're selecting for astronauts, one of the cool things that we can do with precision medicine, hopefully in the future, is and I say cool, but maybe some people be like, oh no, this is terrible because we're just adding another layer of filtering on who can go to space. But we could actually look at and say, hey, this individual who's potentially going to be our next astronaut candidate, we did a genome-wide sequence. We know exactly what each of their genes looks like, down to the base pair level, all the way through every single base pair. And we found out that this individual has 3 single nucleotide polymorphisms, SNPs, where they have abnormal base pairs at a specific point along the chain in a specific chromosome. And this alteration is going to make them 8 times more, and I'm just spitballing a number here, it's going to make them 8 times more likely to have a hypoactive immune system under normal context. And if you're looking at that person who might be the next astronaut candidate, you might say to yourself, like, wait a second, do we really, like, not knowing how this is going to play out, do we really want to select this individual knowing that even despite, completely aside the fact that they're going to be in space where they're getting a higher radiation dose, here on Earth, they're more at risk. Do I want to send this person on a spaceship for a year-long mission? And the answer is going to change. You might say, okay, that maybe we need to go with the other option, the other candidate. Or you might say this person is only safe to go into space for 30 days and not a 180-day mission. You might be able to, with knowledge like that you can get from precision medicine, you might be able to make kind of a health space medicine solution for the radiation problem, in that you're going to be able to know better which astronaut candidates can go up and for how long. And if there is a possibility that they might be at more risk for a problem, then maybe they need to have a special treatment sent up with them. And I'm frankly really excited to see how this line of thought like goes. I mean, it applies to pretty much every issue that you can think of, because at the end of the day, no matter what health problem you're talking about, there's almost always a genetic component to that problem in terms of the susceptibility an individual has to it. But I think in specifics to radiation, I haven't looked at it myself, but because it is known to affect the immune system, one thing that we do know about precision medicine already is just the fact that there are individuals out there who are going to have hypoactive immune systems, or they're going to have hyperactive immune systems. For instance, like they have celiac disease, or they have Crohn's or something.
Yeah, either isn't good. You want it in between. You want it to be normal active. You want it to be not too low or too high.
It might not even be the case that their immune system is hypoactive or hyperactive in such a way that they have a disease here on Earth, it may just be the case that the risk, uh, they're hypo or hyperactive to a degree where you would be a little bit concerned about sending them into space for a long mission. That's my thoughts, and that's kind of my interesting thoughts while reading through this article.
Oh, for sure, dude. That's cool. That's awesome.
There, everyone got their precision medicine dose.
Yeah.
More than enough.
I think this kind of ties in. You talked a lot about selection of astronauts and like kind of which one would be chosen for a short term versus a long term space flight, kind of as like a paradigm. And it actually brings up a question that Vlad sent to me before the show, and that was really like, if radiation is this huge problem, an astronaut or a cosmonaut that has been in space for a very long time might not be resent up into a long duration mission, but yet they are the most experienced for such a mission, and that's like a very valuable like skill to have, like at least emotionally. I don't know, like that it feels right, like the person who's been to the moon before, like you want to be with that person because they know how to do all the stuff. But that person is, for that very same reason, probably the person you wouldn't want to choose from a medical standpoint.
Yeah, like, I mean, the way we have our funding and our costs set up right now, it just seems so prohibitive, right? You're going to be training these professionals with, extremely rigorous selection criteria. They got to be educated. They have to be extremely fit. They have to undergo extreme training. They have to do all of these different things. They got to learn languages, right?
Have to be a Harvard doctor and a Navy SEAL.
Yeah, Harvard doctor, Navy SEAL. You gotta, cured some kind of new disease and I don't know, save some endangered species, right? Like you got to do all these different things, and then you send them out for space for an X amount of time, and then that's it. You can't send them up again anymore because the risks are way too high.
Yeah.
Unless the astronaut wants to go for it, then you're left with an ethical decision on whether or not you think that's a good thing to do, right? Even if the astronaut thinks like, I'm the best, I want to be the first, or I feel horrible because I'm the most trained for it. I don't want to someone else to do it because they might endanger themselves in the mission. So you're left with this dilemma of like, well, man, I don't know.
Yeah, I think like in undergrad I studied philosophy and medical ethics, and I always didn't really know what I could bring to the table for that. And I wasn't really interested in space medicine in undergrad, really. I didn't really know it existed until after I graduated. But like what we're bringing up is there might be a field not only of medical ethics, but of space medical ethics as a thing. So I don't know, like if more people, the more and more people that get involved in space, the more and more people that go to space, it's definitely going to come up, and we're going to be presented with these kind of moral dilemmas, as well as the scientific ones that we're talking about here tonight.
Yeah, and I mean, we could already draw on experiences with. I can't remember if it was with NASA or if it was with SpaceX that there's like a selection of billionaires or millionaires, I think, that were recruited that have put in their their kind of like bet to see if they'll be like the next one to go to the International Space Station. And they're going to be getting their training and they're going to be doing some kind of science on the space station. Then you're left with like the ethic dilemma, like if you have wealth, are you going to be put first as opposed to like,
oh my gosh,
people who are more trained, or people who have the like the resistances necessary, like they have like the beneficial mutations or
we
something.
Talked about this a little bit last time, Vlad, and I think you're so right. Like, just to rehash on that, like, it's really, I mean, in the age of consumeristic private space like the space industry, you're not going to be sending the most fit people up. You're going to be sending the ones who can afford to like fund the mission.
Yeah, right. I mean, should we put an ethical like constraint, like just because you have, I don't know, X amount of money that you're going to be spending on this mission, But you have all these other risk factors. I mean, you've been smoking cigars ever so often. You've been, you haven't been balancing out
Yeah.
The
your
finer tastes
alcohol
in life,
use.
yeah.
You've been just eating caviar and high butter on your bread for like 40 years. Do you want to go? Is it okay to put them
Yeah.
through the
Yeah, I
risk
don't know.
of the cardiovascular remodeling that we just talked
I
about?
think from like a governmental standpoint of like, hey, we're sending up these astronauts who are government employees into space. Uh, in that sphere, yes, NASA has an obligation to ensure that the risks are minimized, right? But I think from a consumer standpoint, and this is just going to be the direction that we go. I mean, Virgin Galactic is already a thing, right? From the consumer standpoint, I think the main thing that's important from an ethical side of view is just that we, as the space medicine physicians, know the risks so that they can be communicated to these people who are potentially clients uh, for space travel.
Mm-hmm. Yeah.
I mean, we'll see.
We'll see.
Yeah, I think whatever boundary, moral, ethical boundary we put up, I think unfortunately a lot of the um, policy barriers that need to be in place often happen after the fact, after a tragedy. They happen
Yeah,
after something we've gone too far and we ran into something that says we really don't want that to happen again. So now we're now we're never going to do that again, and we're going to try and mitigate it beforehand. But I think you can't. It's less of an emotion. Like it's hard to to argue. Like there's this potential risk of this coronary artery disease or this stiff all having um a like a heart attack or having a CVA or having like any kind of problem, like a medical emergency. It'd be hard to argue that from a probabilistic standpoint to say you have a 10% chance. It's like, well, how much more would it have to be to say no to that? It hasn't happened yet. It could be zero.
Mm.
So until it happens, it's like, well, I think it'll be hard for people to really find that boundary, and I think at least in the very early days of aerospace medicine, more on the aero side of things, they use the 1% risk rule, where if you can't exceed a 1% chance for any risk that you're analyzing, you can't like exceed that, or else you can't do whatever aeronautical like flight thing that you can do before.
whatever
I think
thing you wanted to do.
yeah, I think they're moving away from that. I don't think that's a part of the
I mean,
the lore of aerospace medicine anymore. It's not really
it's going to be
baked into them
arbitrary no
anymore.
matter
But
what, right?
yeah, and it might just come down to like whether or not you're going to be litigated against. Like what's the legal recourse? I mean, that's how often medical policies established in the U.S. It's like, well, why did you order this test? Like, well, I didn't want to be. Didn't
Oh,
want
I
to,
assume that
like that's
whoever,
how that works in a way. It's like that's like
whoever
what
it
you're up
is,
against.
whoever it is that's going into space as a consumer, be it like Tom Cruise or like the millionaires or whoever is like funding Elon Musk's SpaceX projects. I'm sure that those people have like a very extensive waiver to sign off. I'm sure they have to waive,
Hmm.
all health and safety,
Yeah,
like everything, like 100%, no matter what.
But is that
yeah.
okay on the organizer's part to kind of like push those kinds of documents? All right. Anyways, that's
Yeah,
not the focus of the talk today. Focus of the
I
talk
think
today is on
it's really
radiation.
interesting though. Yeah, I think it's interesting. But yeah, you're right.
there will be a
It's
radiation clause in the waiver, I'm sure.
yeah. Yeah, and it's like how do you consent an astronaut to or a person like this to go into the capsule like knowing it's like kind of going into surgery. You have to like consent them to surgery. And
Yeah,
it's like
at least
they're
in
going
surgery, you
into
know
this
the risks.
environment that they may or may not really understand the risks.
Hmm.
So it's like there's going to be a pre-flight medical briefing. It's like do you understand that you could suffer all of these consequences and I can definitely see that being a thing. Like instead of like how to fasten your seatbelt, well, maybe that too. I don't know, but it's like the cushion under your seat can be used as a flotation device, and radiation's a hell of a thing, and you might die from it.
Yeah, no, for sure.
You never. I don't know.
Yeah, there's a lot of questions to ask, and I think the important first step, especially when we're thinking about these things for the first time, is just being aware and asking the right questions. Like we can't obviously get the answers now, but at least for the three of us here, when we end up pursuing these kind of environments, we're kind of thinking about, these are the things that we should be aware of when we're stepping into these careers.
Yeah, and I think radiation is like a great place to start out because it really like space in general, space travel in general, it affects every body system, and we've only briefly touched on some of the things, some of the places you could go. Leo, where the International Space Station is, a little bit of the radiation kind of environment there, a little bit of lunar, and we need to learn a little bit more about how it happens on Mars with the kind of magnetic sphere and all that. And then we kind of talked about cardiac remodeling and like how radiation might be affecting that. And then Ryan brought up this great article here that we just kind of went through with like how it could affect the immune system. And so it just feels like we're really gonna have to find out a way to like figure this all out before we could have a sustained kind of presence. So yeah, like that's just kind of there's so much to do in this field.
I think it's like it's like we kind of put it earlier, right? Like either we meticulously put the time in, do the experiments, and figure out what the risks are, and come up with strategies to minimize them, or as both you, Kyle and Vlad mentioned earlier, you kind of just go and do it. Tragedy happens, and then you act.
No, I don't want that to happen.
Yeah, I don't think that'll. I don't want that either. I think that's what'll happen, though. Yeah.
I think that's just kind of the situation.
The inevitability of human impatience.
Yeah.
You don't know what you do. There's the known knowns. There's the known unknowns.
Mm-hmm.
It's just the unknown unknowns that people can't really evaluate.
And then on top of that, it's like no plan, survives contact with the enemy. So it's like you don't even we're gonna do all this planning, and then we're gonna come out of it being like, well, man, that plan was like in retrospect that was a silly plan. Like.
There's gonna be like some alien warship that we had no idea was like orbiting. That like Mars is actually an alien warship.
Could be that what that cigar-shaped asteroid or whatever.
Oumuamua, right? Yeah.
Yeah, I keep getting like stories about how that's actually a spaceship.
Yeah.
But do you guys think that these like the radiation problem is something that we'll deal with, or because it's such a problem where the consequences aren't necessarily immediate? We will more than likely, when I say we, I mean we as a species, are more likely to just send people to Mars, send people to the moon, leave them on the ISS for 2 years, and when they have cancer a decade later, we're just kind of like throwing our hands up in the air. Which of those do you think is more likely?
Man, you're asking a mean question. That's what you're doing.
Yeah. Ryan, you're being mean, Ryan.
I just think that, like, realistically, I think that I think we're characteristically bad at focusing on the long-term problem, like the problems that have a long-term, comeuppance.
Mm-hmm.
I'm kind of the belief that consumerism for other countries, maybe space races, in the future, will be the driver of sending people to this planet, that asteroid, this moon, etc. I'm not sure that something like radiation, the radiation issue, is a thing we'll figure out beforehand.
Of course. Well, and there's so many people who are desperate to make their mark in history as well. Mm-hmm. They will throw caution to the wind to see these things happen.
So many countries.
Yeah, countries and individuals.
Yeah.
Mm-hmm.
They want to be the first. They want to be written in the history books. They're willing to sacrifice anything they can to achieve it.
I think one corollary from my side of things is like the idea that going to the space station, doesn't immediately cause like it does cause problems with bone density, but you don't really have, like, the evidence is, the jury is out in terms of how long it takes for astronauts to begin to have a severe outcome, a fracture, right? For them to like really like seek this. So I think that's already happening, and we're already not doing what we could do, which is provide a medication that is at least a protective mechanism. Some people would want, more rigorous exercise, or the use of a medication like bisphosphonate drugs, or maybe an anabolic drug like intermittent PTH, or different bone drug. But the same could be applied to radiation, where it's like, why don't we just try our hardest to not do this? And then what I would say to that is, even if we do try our hardest to prevent radiation as a problem, a medical treatment doesn't come without its own risks. So, and you have to provide the medication in the first place if it's a long-term, if it's not a shot, and the pharmacokinetics and dynamics are changed in an astronaut due to their volume distribution and their fluid shifts. So it's like, say you have the perfect thing that prevents radiation, well, you have to continue to supply it, maybe, hopefully, or maybe the perfect drug is one that you give on Earth and they're good forever. But like, when are you going to find that? That's not going to happen. So even providing a drug it's really, again, back to this backpack problem, where it's like, do you take a drug? Do you make your backpack better to hold more drug, or do you make the backpack better to like shield you from more radiation? Or do we need to make, do we have humans that are better adapted for radiation? All that kind of stuff. So that's crazy. It just brings up a whole bag of worms that I feel like, we've done, at least on these two orbits. Like, I kind of find myself left with so many more questions. And it's like, this is the reason we do it. Like, the perspectives that you two brought up tonight were stuff I would have considered in terms of like the long-term space, long-term astronaut, both being the person experientially the most qualified, but the least radiation, like, from a radiation standpoint, like already dosed, if they're going to go on another mission. And then all the consequences that were brought up, and the ethics and all of that kind of stuff. So yeah, we actually are approaching orbit. So we're at an hour and 30 minutes. So at this time, just kind of like last kind of final comments. And summaries, and I have a couple other little articles that I'll kind of go into I'll just kind of show that there's a lot more out there to look at, and then I'll kind of present one potential solution that is going up to the space station to get research done about this. So yeah, Ryan, go ahead.
I'm not even sure we mentioned to Vlad the reason we call this an orbit is because we try to do a full show in 90 minutes, the time it takes for the International Space Station to circumnavigate the globe.
Oh, that's adorable.
Isn't it?
That's great.
What we need to do is we need to somehow get an International Space Station tracker up while we're having the podcast on the screen.
You know what, Ryan? I would love to help. I would love to figure that out.
So just like kind of have it going in the background, and we kind of, while we're talking, that would be so cool. We'll have to
space program type thing.
Yeah.
Well, there's websites out there that track it for you live.
That's awesome.
But yeah, that's just a thought I had.
Dude, that's a great idea. Like, it's fun. I like it.
I wish
anything to make you like existentially aware of how insignificant your life is.
Well,
on this planet,
honestly,
knowing
like,
that things out there exist.
Well, it's actually when you talk about space medicine to people, I don't know. I go to the bar, or I used to go to the bar when you could do that. And you would eventually, people ask what you're interested in. If they're, interested in actually having a conversation, they don't just talk about themselves. But, when you talk about space medicine to them, they're like, wow, like, that's crazy, but it's only for astronauts. And I'm just like, no, like, the stuff that we talked on today, like radiation, how many times, how many people do you know in your life who's had cancer? How many times do you know people who need a radiation treatment for any number of reasons? And it's like, this is, how many times have you had to put sunscreen on to go to the beach? And that's to understand skin disorders and all that kind of stuff. So it's when we learn it in the extreme, we can better learn it for every patient here on Earth. So I don't know. That's just kind of my soapbox.
Yeah. Wrap up kind of remarks. I'm just kind of sitting here wishing that we had more time to talk about the other solutions. Like you mentioned, obviously we can select for the best candidates. We can throw up some engineering controls like physical barriers and stuff. But in terms of cancer, you can either resect or use radiation to kill the cancer.
I use radiation to kill the cancer. Right? It's like the Thanos meme.
Causes cancer.
Yeah, it's like, isn't it the Thanos meme or something like that? Where it's like I use the whatever to kill the whatever. And it's like the same thing.
I don't know that one.
Do you know what I'm talking about, though, right?
No.
No, okay.
On screen or something.
All right.
I'm just glad. I hope in the episode that you do corresponding to this, Kyle, that you can cover a little bit more of the pharmacology. I think we only mentioned iodine therapy for someone who received a sudden dose, and that's because there's a lot of iodine in your thyroid gland, and that's something that's just highly susceptible tissue to radioactive activity for that reason.
But in terms of iodine to protect it from absorbing any of the radioactive material.
Yeah, but in terms of chronic radiation exposure, I don't even know if there's a pharmacology solution to that out there. I don't actually know.
Yeah, I don't know either.
Low dose iodine.
It's just not an issue. It's not an issue that you really deal with on Earth.
No.
Not anywhere close to the ballpark where you would have to deal with it in terms of the ISS or the. But I'm sure NASA has looked into that as an option, and maybe sure there's someone out there that we can find who would know the answer. But like someone who, for instance, is already a space medicine physician.
Yeah, I can think of a couple people that I could try and ask. What are the medical interventions for prevention of radiation exposure, radiation dose, or just. I can think of a couple people that know kind of the risk posture. From this investigators workshop, there's a couple people that talked about developing risk models, and I think one of those people would be really good for that.
Yeah, we'll leave leave that for the episode, Vlad, and just so you know, the orbit which we've spent the last 90 minutes talking about. Kyle has been doing kind of an episode that sort of takes all the things we discussed, maybe the highlight reel, so to speak, and kind of lays it out again in a new format. And we'll leave it to him to maybe think
trim the chafe.
Yeah,
exactly.
And potentially even talk about some of the things that we didn't even get time to do because radiation seemed to be such a. Yeah, there's a couple more articles that I'll do a quick slideshow of that I was interested in bringing up, but I'm sure we'll come back to radiation as a thing. So there's an article here that was published back in May of 2019 that looked at MLH1 deficiency, which is one of the genes that encodes the mismatch repair system that deals with DNA, dimers and different kinds of changes to your DNA.
So DNA repair,
and so this, when you lose it, deficiency increases the risk for this hematopoietic malignancy after simulated space radiation. So it was kind of this interesting article.
I don't know what any of that meant. It's like a blood disorder, and
so just a blood derived cancer. So leukemia is the big one that they looked at. But there's a lot of different interesting, cool science that they went into. They had a bunch of cells and rats, and they dosed them, and they did some really cool stuff that I'll be able to talk about. The next thing, I'll do that one last, actually, because that was...
It's got a lot of tabs, Vlad.
Yeah.
We missed a lot of things.
Yeah.
We did.
No, it's all good.
So much to talk about.
radiation was definitely so there was a couple YouTube articles that were or YouTube posters that were presented
Yeah, I
at this
wanted to talk
conference.
about those actually when you're
They're
talking about
super
the
cool, right?
yeah, they were talking about I think it was coumarin,
Curcumin,
hydro,
yeah.
like that. Yeah, is that the stuff that you have in turmeric powder?
I think so. It's an
Oh my
antioxidant.
god, it totally
Yeah,
is.
because
Yeah.
it sucks because it's
Oh, my
not
internet
really
is slow.
bioavailable
Is that the
because it
nutrition
just degrades
perspective?
super easily. But if you get
And you
attached
with
to some kind
black
of
pepper.
nanoparticle,
So what all my nutrition friends talk about is you have to take your turmeric with black pepper. It makes it more bioavailable.
is it though? Does it actually do it?
That's the thing.
Oh. Okay, well, I'll start eating
I
pepper
think
with
you
my
need it,
turmeric.
but
Yeah. 1 second. Let me just pull this up. It's
yeah,
taking.
I wonder if there would be some
That is
nutrition solutions,
is
at least in
pooping
at least an ancillary way to some of these radiation or oxidative species problems.
Mm-hmm. So, I mean, I was so confused at first. I'm like, it can't be that. It can't be
It is,
turmeric
yeah.
powder. And look, it is! It is! They're
I
attaching
mean,
to
think about it, right?
nanoparticles!
Like, you just need when you have free electrons, if you consume things that absorb them easily, makes sense. It's just the key is that they have to enter your body for it to work, and not just
Yeah.
not just pass right through your digestive tract.
Can we inject turmeric? Straight in my veins, dude. Give me that sweet yellow powder.
Get Big Pharma on the phone for that one.
My internet is not taking this at all. Trying to do too many things. Keep talking. Keep going.
Suffice it to say, perhaps
Keep
that
talking.
just have a number of things still that are worth mentioning that hopefully you can get to in the episode, and otherwise maybe anyone watching this can find those links in the about section.
Yeah, I wanted just to pull up the just the title slides so we could just talk about.
Oh, for sure, that's helpful.
But it's taking
Oh,
forever.
got a moment here. I'm gonna give my closing remarks. That seems like you're damned if you do, damned if you don't. It's the immortal paradox.
Oh, Vlad, I'm really glad that you were able to join us for this one. But you have rotation starting. Do you think there's a chance that you might be able to do another one of these in the future at some point?
I think so if I'm responsible. I'll let you know my OBGYN rotations because that's essentially like a surgery rotation. It's gonna be a lot of time that's that I'm gonna have to devote to it. So.
Since I'm doing research, I think anyone watching can expect to see me back in the future on with Kyle. I know Kyle has some other individuals too that he hopes to have on at some point as well. And three seems like a pretty awesome number. Like
It's
I don't know about you guys,
great.
but for me, like I have so much that I want to say that it's like hard. Sometimes it's hard to just like sit and just like wait for my turn. And I'm sure that you guys feel that way when I just go on for like a 10-minute.
Yeah, you guys stole my thunder. I didn't get to talk about any of my articles. No, honestly, it was so nice to have you back. Ryan, thank you so much again for coming back. Like you guys, I need someone to talk about this stuff with. Like I can't do a podcast with just me. I mean, kind of, but like this is much more fun. Like this is like this is like the real show in a way. Like it's just a lot more fun to get people together who are excited about these really interesting questions in space medicine. That like I don't know about you guys, but like by the in my lifetime, I want to see people live on the moon and live on Mars, right? Like that's just a thing that I want. And so it's just like selfishly, it's like let's figure out these things out, and like let's do that. Like let's have a cool, exciting future. Let's do that, right?
It's not just for you. I mean, everyone potentially benefits from what the kind of things that we learn, and the possibility of one day being able to survive should a calamity befall the Earth, having more than one place that we're living. It's all in the long view,
Okay, so these aren't loading, but I can quickly show the titles. So pretty much, one of them did. One of the posters that was really cool was the effects of Mars mission equivalent doses of SCP and gamma or galactic cosmic radiation. I guess that's a double on the GI system. So the GI system is the highest turnover organ of the body. So I thought that was a really cool one.
Sure.
All right, that one's not
Anything
loading.
that has like a high rate of division is sort of naturally predisposed to developing cancer, for instance. If you unhinge that process, then you're in for a world of trouble.
Isolate the nervous system, transplant it into a cybernetic organism, a transhuman fusion of nervous system and robot. And you never have to deal with the high turnover cancer generation anymore.
Yeah, exactly. We just need to be
problem solved.
Yeah.
Problem
solved. But yeah, the last thing I kind of wanted to end on was this article that came out November of 2 years ago. NASA wanted to test this melanin-based. God, what the? Some of these just aren't loading. They wanted to make a melanin-based polymer that could be used on spacesuits, on whatever, coating the International Space Station. And so they wanted to melanin is the pigment in our skin. We all have it at various levels.
Star Trek shenanigans, if I've ever heard it, using like a biology solution to like an engineering problem. That's like their super reverse of the norm right there.
I mean, it makes sense, right? Biology has been evolving solutions to these problems that we have since millions of years ago, dude.
Oh gosh, it's so interesting.
Yeah. Do you really think an engineer is going to figure out something better than life has with the time of hundreds of millions of years?
I mean,
honestly, I'm just happy that, like, as a biologist, I'm not useless in the space realm. You know, like, I've always thought that engineers had they cornered the market, like they just have all the space stuff. But now, since space medicine, it's like that I've learned about it. It's like, oh, biologists, doctors, scientists that are that do all this stuff, you don't have to be an engineer to do this. And actually, even broader, you don't have to be any of this to be interested and to contribute in some way. It's space is for everyone. It's not a zero-sum game. There's room for everyone to be interested in promoting humanity forward. So it's
of course.
It's really it's always really exciting.
You bringing up the idea of engineers and then doctors being important for space development. I mean, thinking about it philosophically, when you go into space, you're removing a lot of the things that create the identity of a human, right? You're removing your environment, you're removing your social interactions, you're removing your vision of nature. So in order to fill in what we have been living with since we were born, artists, authors, creators, musicians are going to have to play an extremely important role as well into ensuring that the soul of the human, or more just importantly, kind of like the psyche of the person, soul if you believe in that, the psyche as kind of like a substitute word. How is that going to remain strong in the face of a ceaseless, endless, what seems to be an infinite void? Even then, that's going to be critical to space exploration and long-term space travel.
Yep. Yeah, that's the, from that's the psychological point of view, but also from a biological point of view, when all these things end up happening to us and, all these different environmental changes, pretty much yeah, exactly. So pretty much
medical model, baby.
Well, it's I mean, I think this is a good place to end, but it's when you go to space, there's all these environmental factors that kind of will end up selecting for different, for people to survive in this. If we have a sustained Martian colony, a sustained lunar colony. Like it's like a set of birds that like are able like one or a pair of them make it over a mountain pass and they have a new different environment on the other side. Eventually they speciate. Like eventually they become like a different species. So like from a large existential question from a more of a biology standpoint, like we will become like we will speciate and like we will become the aliens that like live on other planets,
We will become the
and
Martians.
like do we like will our psyche be able to like stay up with that? Will our culture endure? And my guess is that just as like when people like went across the Atlantic Ocean and made did a lot of bad things, but essentially did some colonization efforts. Like we are not the same. Say you're a direct British descendant from someone who came over. Like you're not the same as someone who stayed in England. Like you're just like we are very different. And so it'd just be very interesting to see if like we unite in all of humanity as this kind of we are humans. Even though we're like kind of different subsects of humans and different planets and systems that we live on. But I don't know, it'd be a crazy wild time, and the medical component is the basis for all of it. Like all of that exciting future, with all of its ups and downs, like it's like the basis is both an engineering and a medical component.
Yeah, rests in our ability to actually make it happen.
Yeah.
And not just be a bunch of people with, cancer and cardiovascular disease.
Yeah.
On the surface.
Broken spirits.
Yes.
All right. Well, do you guys have any other final comments?
I don't personally have anything that I can like shout out. Like this is my thing right now. I don't even really have a Twitter handle or anything that I would like to share. Vlad, do you have like a place where you would want people to reach you if they happen to see this and have questions for you?
I guess just an email.
Or we can just even, go past that for now and say like, hey, this is Vlad from MSU, and if you direct questions to Kyle's Twitter, then Kyle can get to Vlad or me.
Yeah, that'll be perfect.
Yeah.
You took the words out of my mouth.
Yeah, the Twitter account is at TalkSpaceMed on Twitter. And happy to field any questions from anyone. Happy to have more discussion. Over the past like couple weeks, we've gotten up to just under about 200 followers. So it's been getting it's people are
awesome.
Starting to follow it, and it's like I don't know, it's kind of cool.
I mean, I'm here mainly just for me because I just like embracing my inner nerd. But
yeah,
like, the fact that people are interested is pretty dang cool.
Yeah, the metric for success is just doing them. That's what I keep on telling myself. Like, just need to continue to do them. We'll get better. We'll get better. And the whole streaming thing and the whole recording, like it takes me a lot of effort to do it, but I think it's super fun, and we'll get better at it. So.
Oh, for sure.
And thanks so much for taking the time, both of you, and out of your schedules, and super fun to hear your perspectives and hear the questions and things that you're interested in, because as a space nerd, there's nothing better than talking to other space nerds. It's like the best thing.
Yeah, I just have to say thank you so much for inviting me. I'd love to be a part of this.
Yeah, if you know any other medical students happen to be people that usually don't know that space medicine is a discipline that you can go into. There's very few people that usually need someone or something to tell them that it exists. So, if you're listening to this and you're a medical student, please just say, hey, there's this thing called space medicine, and look at this residency from Mayo Clinic, or look at this residency from UTMB. Like, it's a real job that you can do. And it deals with, all these crazy problems that we've talked about. So
I think everyone at Vlad and I's medical school knows about it, because I just can't shut up.
That's great. I mean, you're passionate when you can't stop talking about it, and when you have to make a podcast to talk about it more.
Yeah,
for sure.
Cool.
All right. Well, if you guys can outro yourself, and I'll pick it up after you guys are done.
Yeah, I'm Ryan Penty. Michigan State medical student currently doing a year of research on precision medicine and hopefully space-related precision medicine topics. Right now, I'm mainly focusing on coronavirus, but yeah, interested in talking more about space medicine in the future, learning more, just like everyone else, finding ways to get more of the public aware and interested in the topic, and hopefully, happy to be doing this again in a month or whenever we do it next.
And I'm Vlad, student at MSU. Maybe someday gonna be a cosmonaut, who knows. I love immersion and I love painting. Thanks again.
Damn, we need to talk about that next time. And I'm Kyle Anderson, your medical student / space nerd host. Thank you so much for listening. This is Talk Space Med, Orbit 2, Space Radiation. Don't forget the sunscreen. Thank you so much, and see you next orbit.